I'll try to go 5 minutes over then. Let me begin with a word of prayer. So, Heavenly Father, we thank you for this day again. I thank you for this class and these students. Just ask you to guide our steps today, Lord. In your name I pray, Lord Jesus. Amen. All right, so I introduced the matrix of a linear transformation last time. I have now done the obvious thing and printed out the rest of my notes. So I have the actual honest-to-goodness definition to share with you. The definition I chose was simply this. I said that the matrix of a linear transformation, T beta gamma, is an element of F m by n, implicitly defined by L sub T beta gamma equal to phi gamma composed with T composed with phi beta inverse, all right? Now that is something that we wrote last time. In fact, I proved the equivalence of that and a few other things, right? Now in this context, I'm assuming what? This is for what? This is for T, a linear map from V to W, where the dimension of V is n, the dimension of W is m, as in mummy, and beta is got like V1 through Vn, and the gamma, my typical notation, W1 through Wm, all right? So with that background, that setup, that's how we define the matrix of a linear transformation. Now, so I have tons of examples in the notes, which perhaps we'll get out and look at in a second, but before I do that, let us just prove a few little tidbits about these matrices. So first of all, the properties, very unsurprising. Like if you have two linear transformations, you add them. Guess what? You scalar, if you have scalar multiple out here, you just get C times the matrix plus the other matrix like this. So if we take a linear, we add two linear transformations together, the matrix of that linear transformation is the sum of the matrices of the transformations being added. All right, this is part of my proposition 3.3.10. And that just rests on the fact that the same is true, basically for matrix multiplication. The one that's perhaps a little bit more interesting is proposition 3.311, which concerns, let me try to set it up here. Suppose we have S in the linear transformations from U to W, and T, a linear transformation from V to U, then you guys know the deal. S composed with T is a linear transformation from where to where? T goes from V to U, so from V to W, right? Because T goes from V to U, and then S goes from U to W, so that's the net effect. So just to set some notation here, suppose you got basis beta for, let me see here, I'm trying to keep the notation the same as my notes. I had basis beta for U at the moment. I had basis gamma for V. And I had basis delta for W. So this does not comport with my earlier statement, obviously, right? So that's, I'm saying, suppose you've got basis beta for U, basis delta for W, basis gamma for V. Then if we look at the matrix of S composed with T, right? Notice, okay, so the input basis is what? Gamma. The output basis is the delta basis, all right? So my notation is input, comma, output, all right? And the proposition simply says that, guess what? You can simply multiply the matrices of the linear transformations taken with the appropriate choice of bases, obviously. So like S, beta, comma, delta, and T, gamma, comma, what? So I said U goes with beta, right? Which is just what you'd hope, all right? And like the proof of this, it is pretty much, we can prove it like directly from the definition. If I can do that. So we have left multiplication by S composed with T gamma delta is equal to, according to the definition, phi what? Delta? Okay, composed with what? This, right, as composed with T. Composed with what? Phi gamma inverse by the definition, yeah? Then what we do, so we got the delta and the gamma, beta's got to enter the scene, all right? So you just insert phi beta inverse here, composed with phi beta. I can do that, all right, because that's the identity. All right. But what's this? And I mean, this is left multiplication by S something, right? Composed with left multiplication of T with something. In particular, T beta gamma and S beta delta. I got too many. Those formulas from the previous proposition are not helping me at the moment. Delta beta like that, all right? Because notice the flippity-floppity of the letters. Switcheroo. All right? But here's the thing. We know from 221 that if we have like left multiplication by the A matrix composed of left multiplication by the B matrix, that's left multiplication by the AB matrix. Right? Like if we do LA of LB of X, that's equal to LA of BX, which is equal to ABX, which is equal to L of AB times X, yeah? And that holds for all X. So it's an identity, you see, that this is the left multiplication by the product of these matrices, namely S beta delta and T beta gamma. But you notice that left multiplication, if I have left multiplication of matrix 1, right, and is equal to left multiplication of matrix 2, this implies what? This implies that matrix 1 is equal to in fact, that's an if and only if thing. So the fact that these left multiplications are equal gives me the alleged equality of the matrix, the matrices that I claimed. Yeah? All right. Let me go on to more interesting things. Yep. They're all inside the L. Let me make the L bigger.
Wait, I mean on the right side for the T, is it gamma beta?
Yes. Thank you, thank you. Many thanks. All right, so my larger point here is just that the properties of the matrix of a linear transformation are just what we'd hope for, all right? Like the way they work under addition, the way they work under composition, it's all what we want, all right? Now, we talked about the fundamental matrix subspaces, right? So we talked about kernel and we talked about range, right? So let's think about that some more. But let's think about it with coordinates now. And I want to draw a picture to try to illustrate the idea. So up here, I've got V, I got W, I've got a linear transformation T that goes from here to here. All right? I've got down here Fn, down here I have Fm. Now, where would we picture the kernel? Where would we picture the range? Where are those in these pictures? Do you know? Where should we picture the kernel and the range in my picture? Ooh, these are ancient. I wonder if these can work. Let's see if this works. So, yeah?
Is kernel in V?
Kernel, yeah. So kernel's in V, right? Maybe like this, right? And over here is a W, right? Now I'm drawing them as if they're subspaces, all right? Because they go through zeros in here somewhere, right? They might not be the whole space, right? I mean, if the kernel's the whole space, it's kind of a boring linear transformation. What would it mean if the kernel was the whole space? Well, the range is just zero, but that would mean it's the trivial transformation, right? It just sends everything to zero. That one's really easy to analyze, right? But generally speaking, it's going to be some subspace, right? If the range of T was all of W, then we'd be talking about an onto map, right? Right? So, all right. If we have basis beta, right, and basis gamma over here, then of course I can also trade like this, right? I can map down with the coordinate maps like so, right? And so down here somewhere, I have, oh man, this marker's kind of dead. Oh well. I'd hoped it would live on, but this right here would be phi beta. Oh man, come on. Phi beta, oh fine, I gotta give up on this one. It never really lived. It just went straight from the, I'm gonna give it a shake. See if I can bring it back to life. I won't do it with the cap off because I've done that before. It goes badly. You ever shake a marker with the cap off?
You're doing CPR on the marker.
Yeah. Well,
Does it actually get everywhere?
oh, it'll fly everywhere, yeah, if you get a juicy one. So, all right, you're dead. All right. So, this is phi beta of kernel T. That's right here. And I'm saying like that's this one, all right? I was trying to use some color coding here. I'll get it eventually. And then over here, we have phi gamma of the range of t. All right? Now, of course, we can go from here to here with what? Left multiplication by t beta gamma, as we discussed, right? So t beta gamma, the matrix of t, let's call it, is a m by n matrix. It has matrix subspaces. How are those related to what I've written down? In other words, if I think about the null space of this matrix, and if I talk about the column space of this matrix, how does that fit into this story? So I'll tell you, this, we can prove, is actually the same as the null space of that matrix. And in fact, this is going to be the column space of the matrix. So incidentally, this gives us another tool for calculating, like the kernel and the range for a map. If we choose coordinates, we can calculate the column space and the null space for the matrix, and then we can work backwards and figure out what the corresponding kernel and range was, in principle. Yeah? Now, I haven't proved that these are equal. How would we prove that? Which one do you guys want to work on? We'll only do one of them. The null? All right, so claim the null space of t beta gamma is equal to the image under phi beta of the kernel of t. All right, so let's see here. X is an element of the null space of t beta gamma if and only if what? T beta gamma times x is equal to 0, right? Let me not try. I'm sorry. I was trying to get greedy and do an if and only if proof, but like, I think I'll have better success keeping you guys with me if I don't do that. Let's just do one way. And I think we'll have even better success if we start on that other side. I think that's the easier side to think about. So let's start with x in the image under beta of the kernel of t. What does that mean? Let's see here. There exists, let's say, y in V such that t of y is equal to 0, and the coordinate vector of y, which of course is phi beta of y, is equal to x. Right? For something to be in the image of the kernel, that means that there's some vector that maps to 0 that's in the kernel. And if it's the image under beta, that means that it's actually the coordinate vector of that thing that maps to 0 that we're talking about. All right, so then what? So if I look at t beta gamma times x, what do I get? This is what? This is t beta gamma times what? The coordinate vector of y, right? But last time we proved that the way the matrix works, right, is that this is in fact the gamma. This is t of y, right? Yeah. I promoted that as a way to calculate the matrix at the end of last class, right? Using this formula. But what's t of y? 0. What's the coordinate vector of 0? It's 0, right? So therefore, x is an element of the null space of t beta gamma. So that shows you that, of course, the image is a subset of the null space, right? So to prove the equality, what else do we need to do? Go the other way, right? We want to prove two sets are equal, so next up we'll let see here. Let's let I'll use a different letter. Let me use V as an element of the null space of t beta gamma, all right? Then t beta gamma times V is equal to 0, right? Note, there exists, I don't want to use x and y because I used it in the previous part. Let me use some other letter. How about U? I don't like U. What do you guys want? W? U? What do you guys want? U or W? W? All right, there exists W in V such that the coordinate vector of W with respect to the beta basis is equal to V. Why is that true? The coordinate map is a surjection, right? So, all right, so then I have that t beta gamma times the W, so beta, is equal to 0. But this tells me that t of W gamma is equal to 0, which tells me that t of W is equal to 0, which tells me that W is in the kernel, but notice that V is equal to phi beta of W, right? That's our construction of it. And that means that V is in the image under beta of the kernel of T, since it is mapped to by W. And then the claim follows because we've proved that each set is a subset of the other. All right? Now there may be a more clever way to prove this than what I'm doing right now. I think it's helpful for us to work through these kinds of arguments because it forces us to make contact with all the ideas, you know? But there's probably a more clever way to do it, in all honesty. But here's the thing. So from this, we can see other things, right? Like, notice that we also have the formula, like, range of t is what? If I just wanted to solve for range of t, I could also operate both sides by phi gamma inverse, and we get that it's the inverse image under phi gamma of the column space of t beta gamma, right? And also the kernel of t is what? Solve for the kernel. The kernel is phi beta inverse of the null space. Right? Do you guys remember the rank nullity theorem from 221? Do you guys remember that? What's that?
Didn't we have to use it on mission?
Mission 2? Probably. It is something we know, so it's often useful, right? But like let's think about it here. What does it say here? So notice that like the rank of t beta gamma plus the nullity of t beta gamma. So this is what? This is the dimension of the column space, right? Plus the dimension of the null space. That's what those words mean. That's equal to the number of columns, right? That was the rank nullity theorem for 221. In this context, assuming the counting is the same, assuming that the domain has n dimensions, this is n. But I would draw your attention to the fact that the coordinate maps and their inverses are isomorphisms. Right? They're isomorphisms. So, oh man. Fine, you're dead. I was robbed. That should have gone in. So, phi gamma inverse and phi beta inverse, isomorphisms. What's that tell us? That means that they preserve dimension because they send bases to bases, right? So what does that mean? That means that this is equal to the dimension of the range of t plus the dimension of the kernel of t, because this is like, these are straight up equal. And that's equal to the dimension of v. And this right here, for t, a linear transformation from v to w, this is the rank nullity theorem of abstract linear algebra. All right. Notice that I started with basis. I started with coordinates, but what I've ended with, there's no coordinate. See, because the concept of range and kernel, these are coordinate independent concepts, yeah? So it's kind of, it is interesting. So this proof of the rank nullity theorem in linear algebra, this is not the proof you would see in most people's classes. It's not a good proof necessarily, although I'm trying to illustrate a more larger calculational principle of using coordinates to see things. But we can actually prove this theorem directly. All right, and so I should probably show you that. And so, because this partly answers one of your homework questions, well, not exactly answers it, but it gives you a window into how to do it. Although, I should perhaps talk about coordinate change first. I think I'm going to write out the straightening theorem, and then I will project the coordinate change stuff, because the coordinate change stuff is like more trouble to write. So let's look at the straightening theorem. Let's see if we can prove the rank nullity theorem, maybe do even a little bit better than that, through explicit linear algebraic argument. All right? So I've showed you an argument which is just stealing it from matrix theory. That's what we just did. We just thieved the result from matrix theory, right? You can do that. It's fine. But it's also good to understand how this argument can be framed just in terms of abstract linear independence type arguments. All right, so let me do it. So this is the, and it's a little bit more than the rank nullity. This is what I call the straightening theorem. All right, so we have dimension V equals to N, dimension W equals to M, both finite obviously, and T a linear transformation from V to W. Then the dimension of V equals to the dimension of the kernel plus the dimension of the range. And if the rank of T is equal to P, the rank, by the way, rank is by definition this right here. We define the rank to be the dimension of the range. Notice that our previous discussion shows that that's invariant. Let me say it a different way. It doesn't matter what system of coordinates you pick. The column space is going to have the same dimension, no matter what choice of coordinates you make. It doesn't have to be the same subspace, right? But it has to have the same dimension. Anyway, so if the rank of T is P, then there exist bases beta and gamma, beta for V, and gamma for W, such that the matrix of T beta gamma, it's equal to the P by P identity matrix padded with zeros. In other words, you can choose bases for your domain and codomain so that the formula for the matrix just becomes essentially just project away some of the coordinates and keep others. It's a very dumb formula, right? If you look at it. That's kind of surprising. Any linear transformation, the formula can be rewritten as essentially you feed in T of X and you just drop off the last bunch of coordinates and keep the first P of them. That's weird. And so the proof goes like this. You notice that the kernel of T is a subspace of V. And let beta sub k be the basis for the kernel. And we'll call these vectors V1 through Vk. So let this be a basis for the kernel, right? Extend to beta, and check this out. We're extending in a slightly different way than we usually do. We're extending by adjoining the new vectors at the start. So we're going to put W1 through WP, and then the V1 through VK for V. So keep track of the counting. We're assuming that V is n-dimensional. So what does P plus K have to equal? P plus K must be equal to n, right? If this is a basis for V, it must have n vectors in it, right? So if we got K in the kernel basis, we must have n minus K in the other part. All right. So notice W1 through WP is not in the span of beta K, right? For if it was, if any of those were, what would that tell us? Beta not linearly independent, right? That would mean that we had a linear dependence amongst our basis. That can't be. All right. So then, if I pick x in the vector space, I can write it in terms of the basis. So let's consider x in V. We can write x equal to the sum I equals 1 to P of Ci Wi plus the sum j equals 1 to K. I'm trying to stick with my notation. Oh, rats, I've already... Oh, no, I did that. Did I do that? Oh. Sorry, let me not. I must stick with the notation in my notes, otherwise I'm going to get in trouble here. We don't have time for me to get into trouble. Xi Wi I equals 1 to P. J equals 1 to K of, I'm saying Y sub J, V sub J, right? So if that's the, I can do that because, beta is a basis. And then T of X is equal to, notice that the T of the V's are all 0, right? So since T of X is just going to be equal to the sum, I equals 1 to P of Xi T of Wi. Since T of Vj is equal to 0 for all j, okay? So this says that T of, goodness gracious, T of the set W1 through WP, right, is a spanning set for W. See that? X is arbitrary. This is a linear combination of the TW's that gets T of X. That's an arbitrary point in the range. We just built it from the T of Wi's. So the image under T of these, namely T of W1. So what I'm trying to say is that basically gamma prime equal to T of W1, T of W P is basis for range of T. I have not proved all of that yet. What have I not proved? Like what's missing from that? Can you guys give me like what time, where am I on time? What's that? 5 minutes till the actual end of class, or is it actual end of class right now?
5 minutes till end of class.
So I have 10 minutes then. Okay.
No, 5 minutes until the end of class.
Right, so I have 10 minutes. Cool. Well, we started 5 minutes late. So, all right, so this, now I've only shown that it's a spanning set, right? So we need to prove that's linearly independent, right? So we can show gamma prime is linearly independent, and the theorem follows. Now we should actually show that, but I think the time has come to show it another way here, so. All right, so we're currently in section 3.5, if you're keeping track. Like this is the big theorem in 3.5. Eventually we'll be able to look at it. Come on. Projector, you have one job. There we go. All right. So, don't mistake me running out of class time for this theorem actually being difficult. You can reason through it. Okay, it's not bad. So we want to argue that that's a basis. We've already got that it spans from the calculation above. To show that it's linearly independent, we do what we always do. Take a linear combination equal to 0. Using linearity of t, we have this. But then that means that these guys are in the kernel. That sum has to be in the kernel. Now, if it's non-zero, that's a problem because then you're building these things in the kernel from that, which means there's linear dependence amongst the kernel basis and the rest of the basis, which violates the linear independence that we supposed of beta. So that can't happen. So it must be that this is 0. But if that's 0, then so if that's equal to 0, then we automatically get that these coefficients are all 0 because remember the W1 through WP are a subset of a linearly independent set, and we know that a subset of a linearly independent set is also linearly independent. So because this is, after all, a linear combination of vectors from the basis, and so it implies that C1 through CP is 0. And there we go. That means gamma prime is a linearly independent spanning set. And as such, we have what we want. See, because if you look at the details of the basis that we just constructed, these guys are non-zero, but these things map to 0. Well, I'm sorry, one more step is to extend gamma prime to a basis for W. We have to adjoin things that don't map to 0, which is kind of a hassle for the problem. But what I tell you, use 1 and x squared for that problem. That did work? Oh, okay, you didn't know anybody. Well, it'll work. It's going to work. Anyway, so if we do that, then that gives us exactly what we wanted, which is the identity matrix padded with zeros. So this is, let's put this all together. If you have A and B m by n matrices, and if there exist P and Q invertible matrices such that B is equal to PAQ, then these two matrices are said to be congruent. In 221, we might have called them row equivalent. All right, there's a way to get from one to the other by like row operations. But anyway, two same size matrices are matrix congruent if and only if they share the same rank, which is to say they have the same number of, maybe they don't have to be row equivalent, that may be too strong. I don't think I've actually proved that here, but now let's go back to the other section for the time that remains. Talk about this a little bit. So coordinate change is not bad if we, have the abstract way of thinking about the matrix of the transformation. And so like in particular, what I'm doing here is I'm comparing the matrix with respect to barred bases with the matrix with respect to unbarred. And what I do is I simply switch from one to the other by judiciously like inserting copies of the inverse map. I guess it's up here. So this is the definition for that. This is the definition for that. But you notice what's common to both of these is t. T exists independent of our choice of base. So I can solve both of these for t, and that gives me this relation between the matrix with the bars and the matrix without the bars. And then I simply solve this equation to get that one. And that shows me how to change basis, going from one choice of basis to a different choice of basis. I have to multiply by these change of basis matrices. Now, in the context of Rn, if you're using the same basis in the range and the domain, this is what produces that P inverse AP thing we did in 221. But it's much more general than that, because these change of basis matrices aren't even the same size, possibly, in this context. Like this could be 2 by 2, this could be 3 by 3 or something, right? I have an example like that. So here, see my V is 3-dimensional, my W is 2-dimensional. See, it's in a dumb picture, but there it is. So like here is an actual, honest to goodness, gory example that would take me an hour to write out. This is my linear transformation from quadratics to apparently complexes. It's linear. And so I sort through my choice of this basis, this monomial basis, that complex basis. Here's the matrix, all right? On the flip side, I could use this monomial basis, x minus 2 powers, and I flipped the I and the 1 just to make it different, all right? Different choice of bases. And then I go through and I calculate the matrix with respect to that choice of basis for my linear transformation. And I get something else. But what I'm doing here is this is the change of basis going from one to the other. When I actually calculate this, I get that matrix. And, watch out. Anyway, I get to the point here. So I actually worked it out. And if I go through this is, I calculated that, and I work it out, and I get this. On the flip side, of course, I can just calculate that directly and show that it matches. But if you look at this, and here I just did it directly. I'm just finding the formula, the matrix with respect to the barred bases directly from examining formula in terms of the barred bases. Input in the barred basis, output in the barred basis. What matrix does it take to get from this? This has got coordinate vector ABC in the barred basis. This has coordinate vector, I forget which one I put first, I or I can't remember what gamma bar was, but anyway. The point is that you can either calculate it directly or you can do the change of... Now, I don't actually change coordinates like this that much. It's mostly of a theoretical interest. But the larger point is that we have now a rule for how to change coordinates for a matrix, and this is how it goes. And this is how the results descend to just like column vector, like a matrix on column vectors. This is how that goes. But so we'll need this later when we come back and talk more about eigenvectors and stuff. But anyway, that's all for today. So go away now. Let's see here. Heard that somewhere.
I have a physics question for you.
Wait a minute. I only gave you 50 minutes of lecture. That's lame.